Hello kids! Today we are going to be rocket scientists. We're going to design, build, and launch straw rockets. Since this may be your first experience as a rocket scientist, we should probably discuss what rockets are and are not. Simply put, a rocket is an object that is designed to be propelled through the air. Some rockets are propelled or pushed forward by a rocket engine. We will work on that activity another day. Straw rockets are propelled by rapidly forcing a blast of air into the opened end of a straw rocket. The rocket moves forward according to Newton's third law of motion. For every action, there is an equal and opposite reaction. The force of the blast of air is the action. The forward movement of the rocket is the reaction. I am sure that many of you have experienced this type of rocket before, a straw with a paper cover. If we tear open one end of the paper cover and blow into the opened end of the straw, the paper cover becomes a rocket. The action was the force of air blowing into the straw. The reaction was the paper cover moving forward. Okay, so now that we know what a rocket is, let's look quickly at what a rocket is not. This is a rock-it, not a rocket. This is a rock-kit, not a rocket. We will rock it, not a rocket. That's quite enough of that. Let's get started with our straw rocket activity. Here are the materials we will need to design and build our straw rockets. Precision straws, index cards or construction paper, modeling clay or poster tack, scissors, tape, and a ruler. For designing our rocket, we will need paper, pencil, and a few ideas. For launching the rocket, we will need Pittsco's straw rocket launcher. Our rocket design will need to meet some basic guidelines or specifications to be stable and to fit the launcher. Here are the specifications for our straw rockets. Straw diameter must fit over the launch tube of the launcher with very little gap. Minimum straw length, 10 centimeters. Maximum straw length, 20 centimeters. Minimum number of fins, 2. Maximum number of fins, 5. Maximum number of clay and tack, 2 centimeter diameter ball. Using our pencil, paper, and ideas, let's sketch a simple straw rocket. Let's begin by sketching a straw on our paper like this. It doesn't have to be exact. This sketch is just to get an idea of what we want our rocket to look like. The straw is the main body of the straw rocket. Now we need to add some fins. Let's use 4 fins, but let's sketch some different fin types to determine which kind we want to add to our rocket. Here is a simple triangular fin. By changing the lengths of the sides of the triangles, we can easily change the fin shape. This fin is more rounded and looks a lot like an old-fashioned rocket ship from early science fiction cartoons and movies. Notice that the fin has one straight side that will be the attachment point to the rocket body. For our rocket, let's use a simple triangular fin shape like this one. Now that we know there will be 4 fins and their shape will be like this, let's add the fins to the sketch. Fins are usually very close to the bottom of the rocket. The last detail to add to our sketch will be the nose cone shape. Nose cone shapes can vary. They may be a simple cone like this, a rounded cone like this, or a simple rounded ball like this, or many other possible shapes. Let's use a simple cone shape for our rocket. We will add it to our sketch. Here is what a built rocket should look like. At this point, you may want to brainstorm and come up with 2 or 3 more rocket designs and sketch them so you can choose the one you want to build. Be sure to keep in mind the specifications that the final rocket must meet. We have our sketch and are ready to begin building our straw rocket. Let's begin by checking the straw diameter to be sure it will work on the launcher. If you're using the precision straws, they should fit just right. If you're using ordinary drinking straws, be sure to test the straw on the launch tube of the Pittsco straw rocket launcher before you proceed further. If the straw does not fit over the launch tube, or if there is a gap between the straw and the launch tube, then try a different straw, or use a precision straw from Pittsco. Once you have checked the straw diameter, be sure the length of the straw on the sketch meets the specifications. The length is about 15 centimeters, which falls between the minimum and maximum specifications for the straw length. So using scissors, we can cut our straw to 15 centimeters. For our fins, we will need to make a fin pattern by drawing the fin shape on an index card or construction paper. Once we have the shape drawn, we can cut the pattern out and use it to draw 3 more fins. You may want to orient the fin shapes to make the best use of the paper by rotating the fins in different directions. This process is called nesting. Once we have 3 more fin shapes drawn, we can cut them out, and now we have 4 identical fins. Having 4 fins also meets the specification for the number of fins for a rocket of at least 2 fins, but no more than 5 fins. We are now ready to attach the fins to the rocket body. As we assemble the fins to the rocket body, we need to be sure that the fins are equally spaced around the straw. Since we have 4 fins on our rocket, there will be 4 equal spaces around the rocket body. This means that the fins will be at right angles to each other. To attach the fins to the rocket body, we can use cellophane or masking tape. For each fin, we will need a piece of tape that is the same length as the side of the fin that attaches to the rocket body. We carefully attach the tape to one side of the fin so that the tape hangs over the edge of the fin halfway, like this. Once the tape is attached, we are ready to attach the fin to one end of the straw, which will now become the bottom of the rocket. We will try to line up the fin with the straw as accurately as possible and press the tape to the straw. If the fin seems crooked, then you may want to carefully remove the fin and reposition it. Our second fin will be attached in the same manner, but on the opposite side of the straw, like this. The third and fourth fins will be attached so that they are opposite of each other and are at right angles to the first 2 fins attached. After all the fins are attached, we will do a visual check of the rocket, looking at the bottom of the rocket to be sure the fins are evenly spaced around the rocket body, and looking at the sides of the rocket to be sure the fins are in line with the rocket body. We will carefully trim away any excess tape on the fins with our scissors. We are now ready to form a nose cone and attach it to the top of the rocket body. To form the nose cone, we will get a small chunk of clay or tack and roll it into the shape of a ball. According to our specifications, the diameter of this clay ball should be 2 centimeters or less. The diameter of the ball is the distance across the ball, which for this clay ball is about 1.5 centimeters. So it meets our specification. Using our fingers, we will form this ball into the nose cone shape we originally designed. We will want the nose cone to be smooth to help the air flow smoothly over the rocket. Once we have the nose cone shaped and smoothed, We will attach the nose cone to the top of the rocket body by carefully pushing the end of the straw about 1/2 centimeter into the clay. Again, do a visual inspection of the rocket. Be sure that the nose cone is centered on the straw. If necessary, the nose cone can be removed, reshaped, resmoothed, and reattached to the rocket body. Let's compare our straw rocket to our original sketch. I can see a certain family resemblance there. Our rocket is assembled and is ready to launch. Let's take a look at the Pittsco straw rocket launcher to see how it works. The straw rocket goes over the launch tube, which can be set at a variety of angles. The size of the angle can be read from the scale on the launcher. The launch tube is connected to the bottom of a plastic cylinder, which holds a calibrated launch rod. The launch rod is lifted to the desired calibration line and is dropped, compressing air underneath it and rapidly forcing the air into the launch tube. The air is trapped in the launch tube by the straw rocket that is covering the end of the launch tube. Once enough air pressure has built up in the launch tube to overcome the mass of the straw rocket, the rocket launches into the air at the set angle. Let's try an actual launch with our straw rocket. We will place the straw rocket over the launch tube and carefully slide it down the tube until it stops. We will set the launch angle to 80 degrees, pull the launch rod up to the second calibration line, and release the rod, sending the rocket into the air. Wow! We really are rocket scientists. Our rocket flew into the air and then came back down due to gravity. Kids, here are some troubleshooting tips that may help you if your rocket did not fly well. Be sure the nose cone completely covered the top of the rocket body tube. It cannot let air escape or the rocket will not launch completely, or maybe not at all. If your rocket is heavy or large, you may want to pull the launch rod higher to provide more force to launch your rocket. Another alternative is to decrease the amount of clay that you used for your nose cone. If your rocket wobbled in flight, it was unstable. You can make the rocket more stable by changing the amount of clay used on the nose cone, changing the shape or number of fins, or by changing the length of the rocket. Once you have a working straw rocket, you can begin collecting data for your rocket. For instance, you may want to find the mass of your rocket, the total length of your rocket, and the diameter of the straw rocket, including the fins. This information can be helpful if you build more than one rocket or if you look at the data for all the straw rockets built in your class. Data for your launches should include the launch angle and launch rod calibration mark. Depending upon what data you want to look at, you can also include the range, that is the distance the rocket traveled, and the altitude, the highest point of travel in the flight of the rocket. Let's look at the flight of a straw rocket. When we drop the launch rod, the rocket takes off at the angle set on the launcher. As gravity pulls down on the rocket, the angle of the rocket gets smaller as the rocket reaches its highest point, the altitude. The rocket continues its flight and is pulled down to the ground. The distance from the launcher to the point of touchdown is the range. An easy way to determine the touchdown point is by using a roll of white paper or craft paper to cover the landing area. When the rocket lands, since the nose cone is more massive than the rocket, it will usually land first, with the clay leaving a mark on the paper. Measuring from the mark back to the launcher will provide you with the range data. You may want to have a range spotter help you determine where the rocket lands. Once there are a number of launches, it may be difficult to determine between marks. Another option is to label each mark with your initials and a launch number. You can collect data on your rocket, measuring the range, while changing the launch rod height and keeping the angle set the same. Your data table might look like this. The red numbers are made up and would be replaced by your actual data. Once the data table is complete, you can graph the data on a graph like this. The black dots represent the range for the rocket at each launch rod mark. You can see that as the height of the launch rod increases, the range of the rocket increases as well. In fact, if we drew a line between each dot, we would get a graph like this. All the dots connected make a nearly straight line. When data points make a line, it is referred to as a linear function. For each increase in the launch rod mark, you will see an equal increase in range as you go from point to point. In a linear function, the slope of the line, or the amount of vertical rise in the line for each amount of horizontal run, is the same for all the data. Sometimes, actual data will be slightly off from what the scientific formulas would predict. For instance, in the data for this straw rocket, if everything had been exactly as expected, the range for the launch rod mark of 2 would have been exactly 200 rather than 205. Graphs are a useful mathematical and scientific tool to model or predict what will happen. For instance, without actually launching the straw rocket, what would we predict the range of the rocket be if we raised the launch rod to halfway between the 3rd and 4th mark? If we look at our graph, halfway between the 3 and 4 mark would be along this vertical line. The point where this vertical line crosses our data line is here at the red mark. If we look back to the left side of the graph, we see that the range would be about 350 centimeters. Kids, there are a number of activities that you can do with your straw rockets, data tables, and graphs. Here are some activities that your teacher may have you do individually. 1. Using the same drop height or launch rod mark, try launch angles between 10 and 90 degrees to determine the launch angle that provides the greatest range. 2. Using the same drop height or launch rod mark, try launch angles between 10 and 90 degrees and determine the launch angle that provides the greatest altitude. 3. Build 4 rockets of different lengths but use the same nose cone shape and fin shape. Launch the rockets at various angles and launch rod marks and determine the rocket with the most range and the rocket with the greatest altitude. 4. Build 4 rockets with different nose cone styles or sizes, keeping the length and fins the same to determine the effect of the nose cone shape to range and altitude. 5. Build 4 rockets with different numbers of fins, keeping the length and nose cone styles the same to determine the effect of the number of fins on the range. 6. Using the information gained in these experiments, design a rocket that will travel as close to 600 centimeters as possible. You will need to determine the launch angle and launch rod settings to come as close as possible on the first launch. See how many launches it takes to achieve the 600 centimeter range. There are also some interesting activities that can include the entire class. 1. Use the same launch angle and launch rod settings to launch each rocket in the class. Record the range of each rocket in a data table. Also record the mass of the rocket, the length of the rocket, and the number of fins. Determine the average range for the class and graph the data to show the range versus mass, range versus length of rocket, and range versus the number of fins. 2. Have a class competition to see who can construct a straw rocket that will come closest to a range selected by the teacher. The design should be based on class data and individual student data. The launch angle and launch rod settings may be pre-selected by the student. Kids, I have enjoyed this straw rocket activity. Please fasten your seat belts. Move your tray tables to an upright and locked position. We are ready for launch into the straw rocket activity. Launch angle set, launch rod set, T-minus 5 and counting. 4, 3, 2, 1. See you real soon.